Good morning, good afternoon, or good evening. This is now question 2 of the Step 3 2024 paper. As with all of these videos, the aim is to show how to tackle one of these questions and to give some of the thought processes, the exam technique, the error spotting ideas, which will be incredibly useful as you go and tackle such questions yourself. You should only be watching this if you've already had a go at the question and you either completed it successfully, well done, or you've got stuck somewhere and you're looking for some kind of hint. As soon as you get such a hint, you should pause the video, go back and try and use the idea to take your own solution that little bit further before watching the rest and spoiling the rest of the solution. So here we have a question we're solving inequalities, inequalities which are involving square roots and moduluses. So nice thing about it is modulus equations really are two inequalities. We can have an upper and a lower bound all built into one of these questions. So really this first inequality, we're bounded between negative the thing less than or equal to the square root of 4x squared minus 8x plus the 64, and the positive of the thing. That's exactly what that modulus is really telling us. We're somewhere between those values. Well, that, and you may have wanted to do this immediately, if we just square everything, we can actually get rid of the modulus immediately, and then this quadratic can just be less than or equal to x plus 8 squared. And you can kind of justify that by breaking the modulus into two halves. And one thing to be careful about is this now has to be greater than or equal to 0. If you square something between two values, then you are still above 0. So now we actually have a quadratic inequality to solve. I don't know if I want to deal with the greater than 0 aspect. I probably do. And if I look at part A and part B, they are the same left-hand side. So I only really need to do it once for the part A and part B. So I might as well do that once. So then the left-hand inequality, we have a common factor of 4. I'm hoping this is going to be a really quite a nice one. So divide through by 4 plus 16. 16. Now this isn't going to give me a nice solution, is it? So I'm tempted to actually complete the square here. Complete the square allows us to kind of look at minimum points, and as I'm greater than or equal to 0, knowing the minimum point is quite useful. So completing the square gives me a so, and that's actually always true, which is true for all x. So that lower bound actually isn't going to make any difference whatsoever. No matter the value of x, we are fine there. Good thing to check. The right-hand inequality then is the one that's slightly more interesting. We've got our 4x squared quadratic is less than or equal to, expanding that side out, plus 16x plus 64. The 64s are cancelling, that's quite nice. So 3x squared minus 24 is less than or equal to 0. So you can factorise that into an 8 and a 0. So now we have the quadratic with a solution at 0 and a solution at 8. We want that quadratic to be less than 0. So that gives me 0 is less than or equal to x is less than or equal to 8. Nice. And I could do some checks. I could go and sub 0 back into here. And that would give me that the square root of 64 is less than or equal to 8. That's good. I could sub 8 in and see what happens. I'm expecting this side will be equal 16, and then that side 16, so everything worked out fine there. Okay, so part A sorted. There wasn't actually anything unpleasant with that part A whatsoever. Fairly expected. I tend to start by giving you a chance to play with the idea before starting to put the subtleties in. Part B, if we do exactly the same thing, let's square both sides. So this is less than or equal to 3x minus 8 squared. And I'm not going to worry about the greater than or equal to 0 this time. We've already shown that that was always the case. Expanding out the double bracket to again a 9x squared minus 48x plus 64. So this time I want to move stuff to the other side. So this will be 5x squared minus 40x. So that's 5x, x minus 8. Which are the same solutions actually that we had in the previous picture. We have our solution of 0, let's draw that slightly better, 0 and 8, but this time we want the quadratic to be greater than 0, so that's going to give me that x is less than or equal to 0, or x is greater than or equal to 8 as my solution set. Nice. Now it might be worth, and you can try this if you want, sketching these graphs to kind of think about what exactly they are doing, and that will be a useful activity, mostly because some of these questions actually require you to sketch them. I won't do that here. Best way to sketch the left hand side is to complete the square and to consider it as a transformation of just the square root graph, just root x, and looking at it as a translation of the root x graph. Carrying on with the question itself though, we're now on to part 2. We're having an f of x is something that looks very similar to what we've already dealt with a few times, this square root, but now we're subtracting something which we haven't considered yet, 2 lots of x minus 1, and we want to think about this other thing. So let's consider we're doing the square root of plus rather than minus this time, and we're timesing that by the f of x. And this shouldn't surprise you as something that's quite useful to do, because it's basically rationalizing the denominator. We're timesing by the same thing with the opposite sign. We're basically setting ourselves up with the dots. So expanding this out, the square root times the square root cancels the square root. Both of the middle terms, that times that is a positive, that times that is a negative. They cancel out perfectly, exactly as we expect dots to do. And then we're left with minus 4 lots of x minus 1 squared. So let's expand and simplify. This is going to be minus 4x squared. We're getting a minus 2x, that's a plus 8x. And then a minus 4 on the end. Lots of things cancel, which is kind of why it suggested that we write it as so. So then we can write, so then we can actually say that f of x, which is this bracket here, we can actually write in the relatively silly way as 60 over the square root of plus 2x minus 1. And now we want to try and work out what happens when x goes to infinity. So as x goes to infinity, let's think about what happens in the denominator. We could hand wave a little bit, but again, I've kind of suggested this a few times, is complete the square. If we complete the square on this, I'm actually going to do it in a slightly silly way. instead of factorising out the 4 first. And if I do double check, yep, that does give me the correct first 2 terms. Need to add 60 on the end. I'm actually going to complete the square with a 2x inside, not an x inside. Fewer steps, and it gives me the same solution. So as x goes to infinity, this thing here is going to infinity. So that tends to infinity. So f of x equals, or tends to, well, equals 60 over the square root of something going to infinity plus 2 lots of something going to infinity. So this goes to 0. And you should probably write that a lot better than just scribbling as so. So this f of x, which is this weird function, as x becomes bigger and bigger and bigger, this gets smaller and smaller and smaller. So now the question's asking us to sketch. Okay, so it did actually require us to sketch this curve. So I'm going to write y, and I'm going to write it in a slightly better way this time. I'm going to factor out the 4, so that's minus 2x plus 16, and then complete the square, so this is x minus 1 squared plus 15. And now I can think more clearly about what that is as a sketch, as a function. The normal x squared curve, sorry, the root x curve is a kind of quadratic on its side. But if we look what we've done here, this is translated by a vector of 1. It's not even 115 even, because that's even more awkward because it's underneath the square root. But it's going to be this kind of shape, centered. Well, this bit here is equal to 0 when, or minimum, I should say. Dupe is minimal at x equals 1, and then the y value is 2 root 15. So that's telling us what this bottom point of the quadratic is. Now, it's not really a bottom point because our quadratic's on its side. It's kind of our furthest left point instead. So when x equals 1, our bottom left point is at 2 root 15. So we have a kind of a quadratic, half a quadratic, because in writing the square root symbol, we've assumed we're taking the positive square root, whereas the normal quadratic has both the positive and negative roots. So that's my unpleasant curve. And if I also want to sketch on the same 2 lots of x minus 1, well, that is going to cross the y-axis at minus 2 and the x-axis at 1. So we're going to have a solution, a drawing as so. Now I'm a little concerned because when these two curves are equal to each other is exactly when f of x equals 0. But f of x, it could be, I suppose it could be equal to 0 at other points, but this condition that we've said here is when x becomes huge, these two curves look similar. So actually these two should be asymptotically equal to each other, not actually intersecting. So I should probably draw these in a slightly better way to show the fact that they're not actually going to meet until infinitely in the future. And I should probably made the steepness of these slightly better. But these are going to be asymptotically equal rather than actually intersecting. So they kind of intersect at x equals infinity, which is a nonsense thing to say, but that's what's going on. Okay, so that's part I and double I done, and we're going to move on to the next part. So part 3, now has another more general equation, and this time they want us to find the value of c such that the solution set is given as so. So we've kind of solved this exact style twice with the less than or equal to the mod of x plus 8 and less than or equal to the mod of 3x minus 8, and we got the solution sets in both of those cases. The one thing I'm a little worried about is the fact this is only a one-sided inequality, whereas both the solutions we had before was a sandwich and a double-sided inequality. So somehow we need to fix it so not all of the solutions are valid. And actually, no, I'm okay. I was just a little worried about this solution here for a moment, because when I sub in x is 0 into this, I am actually using the modular sign to flip the inequality to get a positive 8, but this side does give the positive 8 because it's a square root. So there was no official problem there. But something to be worried about. Sometimes when you do that squaring trick, you can create additional solutions that you didn't want. Okay, let's actually tackle this question then. So let's do the same as we've done every other time. We have squaring both sides. So this is less than or equal to, and I'm going to expand out the bracket straight away actually, 2mcx plus c squared. And noticing this is a different square root, so I should have this greater than or equal to 0 condition, which I've kind of half referenced a couple of times. Now this has to have a solution of x being greater than or equal to 3. Now I am actually going to solve that left-hand side inequality again. Does this quadratic factorize nicely? No, and it does actually look like if I complete the square, this will be 4 lots of x minus 5/8 squared minus the 5/8 plus 4. That's always going to be positive again. Even when I expand that out and add on the 4, I've got a square number plus a positive number. That's always positive. So again, I'm not going to need to bother dealing with that greater than or equal to 0. But I do want to have a solution of 3. Now I'm pausing because I still don't like the fact that this is only a one-sided inequality. Whereas I would have probably expected or hoped that this would be a two-sided inequality. And I'm trying to think what the graph might be doing to fake that solution. And if I do consider this graph, the left-hand side is some kind of half quadratic, the right-hand side is some kind of V shape, and yeah, here's where that extra solution is. If we continued this fake quadratic, which we've kind of you do when you square both sides, you get rid of the fact that you're taking the positive root by squaring it, we get an extra fake solution here that we didn't want. So we're going to have to be slightly aware of that as we try and solve the rest of this. And I'm going to leave that picture there as I carry on with the algebra. So I want this to have a solution of 3. So we expect equality when x equals 3. So if I sub 3 in, that's going to be 4 times 2, so that's 36 minus 15 plus 4 is less than or equal to 9m squared plus 6 mc plus c squared. This is going to be a little awkward to try and get a solution out of this because I've got two unknowns. I mean, I could have actually subbed in the 3 before I squared both sides. Maybe smart. Actually, definitely smart if I look. If I calculated that number on the left-hand side, subbing 3 into this, I'm getting a square number. So let's actually do 4 lots of 3 squared minus 5 times 3 plus 4 is going to be equal to 3m plus c, the modulus of. So I want to, that's 36 minus 15 is 21 plus 4. So this side is just 5 equals 3m plus c. Find the value of m, and so another hint from the question, find a value of m and the corresponding value of c, such that the solution set of that is as so. So I could just make up an m. So I could pick m equals 1, c equals 2. That works for this. And if I look back to my picture, is that going to give me only one solution? Well, if I do, what did I say? X plus 2 would be my equation. That's going to have a solution over here, minus 2. It's got one solution. Well, it's going to have probably 2 solutions. So if I could enforce that this point here is positive, the vertex of my V shape is positive, then does that force there only to be one solution? Well, certainly if I put that root further this way than the minimum here, well, that minimum here was when x was, if again I imagine completing the square, the vertex there is when x is 5 over 8. So as long as my solution there is bigger than 5 over 8, so I can't use this setup. I kind of want the c to be negative. So if I take m is 3, c is negative 4, that means my solution there will be at 4/3, and that's only one solution. And then that's then going to work. So then we've got the graph will then look exactly as we want it to. We're going to have our half quadratic, with that being 5/8, and then the V shape with its base at 4/3. Oh, but we could potentially get another solution over here. And that's not good, is it? We potentially get another solution from the negative side, and then we could get some of this, or really some of this. Now how? This V shape is still concerning me. Because no matter how I draw this V shape, no, I suppose, and I'm probably thinking too much into this, we can only have this hang on, every x value is giving a solution. So am I drawing this shape wrong? No matter the value of x I put in, I'm always getting a positive answer. Oh, I'm enjoying that graph wrong, haven't I? Definitely drawing that graph wrong. It's not based on a root x graph. Now the root x graph does look like that. It's based on a root x squared graph. And a root x squared graph is a lot more complicated. So that's going to mean that this picture over here, which should have felt more awkward than I originally gave it credit for. Now we certainly still have a minimum at that point, but it's going to be more, and this is what the asymptotic nature is giving off. So we've got our minimum at this point, and then if we take a quadratic and we square root it, we're making it shallower, so we're getting probably something that looks a bit more like that, and that's where that asymptotic nature is going. If I sub 0 into this, I am intersecting there at 8, which is only a tiny bit higher than 2 root 15. So, okay, so the square root of one of these is actually a shallower looking quadratic, which looks like it becomes linear in the end. So really this graph here, it still has its minimum at that 5/8, but it's going to be, it's got a solution at 4, so it's going to be this kind of shallow quadratic style shape. So I still have to have that condition. That condition still has to hold. And I probably want to try and think about what part 2 is saying. Part 2 is actually more saying that as we go off to infinity, we're kind of asymptotically becoming these kind of this V shape. Now, if I can match this yeah, I'm kind of having to shift. If I shift this V shape along, this asymptotic nice V shape that we've created, if I shift it along, it'll have a collision on this branch, but it will never touch that branch. So I actually want to work out the kind of asymptotic behavior of this 4x squared minus 5x plus 4 all rooted. And if I look at where this came from, this actually was exactly the completed square part of this thing here. So if I do the same thing, this is going to look like 2 lots of x. I need the minus 5/8. So this is the 4x squared minus 5x plus 4. I'm now writing in a really silly way. Let's put the square root on. I'm going to double check that this does expand. That does give me the 4x squared. That times that is giving me minus 5/4, which is way too much, which is way too small. So I want this to be minus, I think, 5/4. So that when I multiply by it, I get minus 5/2. There's 2 of them. Lovely. Plus, I don't actually care what that thing is. So this is asymptotically 2x minus 5/4. So that's going to be my orange lines. So now I just need to shift that to the left slightly so that it satisfies this condition here. So then let's let m be 2, so the gradient matches, and then c can be minus 1. Now, has that shifted in the right direction? Yes. This crossed the y-axis at -5/4. This is crossing the y-axis slightly higher up if it were to go down to the y-axis. So I have shifted that V shape off to the left slightly. It's intersecting at the right point. That pair does indeed work. We're not getting any solutions on this side because we're outside the asymptotic behavior, and we are getting a solution on this side because we're intersecting. We were the asymptote and we've shifted over far enough to make 3 my solution where I cross. Okay, part 4. And part 3 was much less pleasant than I originally thought it was going to be. Part 4. Find values of P, Q, M, C such that the solution set of that inequality is that stuff. Okay, well, it's now actually a modulus rather than a square root. So that's going to make our lives maybe slightly more pleasant. So the first thing in my head is consider the picture very carefully. What exactly is going on here? We have a quadratic, but we've got the modulus of a quadratic. So we've got a normal quadratic shape, but the u that goes below the y-axis has bounced up. And we have a straight line which is intersecting in 4 places. I'm actually going to make this quite a lot larger to make it a bit more obvious where I see all those places. These solutions maybe will be relevant later, but they're definitely not the P or the Q. And our straight line is going to do something so that it crosses every single aspect of the curves. And our solutions, we want where the straight line is above. So this is -5 to 1. My axis is in the wrong place, but I don't really care. And then 5 to 7 are those coordinates. Now I could set up 4 simultaneous equations in 4 unknowns. When I sub each of these in, I'll have equality at those points. I need to be a little bit careful because these 2 solutions here are where the quadratic has flipped. But is there a smarter way? I could try and think about something that the question's already done. This does feel a little bit different to the rest of the question. I don't have the square root of a quadratic. And I don't really fancy square rooting this equation to get the square root of a quadratic. So I'm not going to. I think I'm going to try writing out the equations and seeing what happens. So let's pick out each of the equations. When x equals -5, that's when the quadratic was nice, was behaved. So that's 25 minus 5p plus q equals -5m plus c. When x equals 1, this is when the quadratic flipped. So I'm actually going to flip the linear side. So this is -m minus c. When x is 5, that's when the quadratic again was in its flipped state. But again, I'm going to flip the other side. And then finally, when x is 7, the quadratic is in its normal state. So there's no flipping. And you can see that these middle 2 equations are the ones which are flipped, making things work out. Now, how can I solve quadruple simultaneous equations in 4 unknowns? Lots of ways to do it. I'm already seeing that if I add or subtract some pairs of these equations, certain things cancel. I would quite like to get to the point where I just reduce the number of unknowns and try and see if there's any tricks that I can do. In particular, looking for things where I can simplify my unknowns. So are there any combinations of variables which always appear in exactly the same way? We almost have that with the p and the m's. They're the same there, they're the same here, but then they're opposite on these middle two, which again isn't surprising because that's where it flipped. We also have a lot of ways to cancel the c's out. Some of those ways may also cancel the may cancel the q's out, or even the p's. Trying to think what the best, most efficient technique is, but at this point we might as well just go for it and hope that some things cancel, and cancel in the most pleasant ways possible. So I'm going to do equation 1 plus equation 3. That's going to kill the c's. That's going to give me 50 plus 2q. The p's have cancelled, equals minus 10m. If I do equation 2 plus equation 4, that's going to give me 50 plus 8p plus 2q equals 6m. Okay. Well, I've got 50 plus 2q in the second equation, which is a minus 10. So that can tell me that 8p equals 16m, or p equals 2m. That's a helpful thing potentially. So I've got a link between p and m. I can use that to cancel all the p's out of somewhere. I can't, if I sub this straight back into here, the two equations will become identical. So I kind of want another equation that's linking, that's got rid of the c. So I could do equation 1 and equation 2 if I add those together. Let's see what happens. So 1 plus 2 is going to be 26 minus 4p plus 2q equals minus 6m. So if I substitute my p in, that's going to be a minus 8m, so that's going to equal 2m. 26 plus 2q. And now if I call this equation 5 and equation 6, if I do equation 6 minus equation 5, this is now just careful manipulating of all of the stuff. We're getting that's going to be negative, isn't it? Negative 24 equals 12m. The other things cancel. So that means that m has to be equal to negative 2. That means p has to equal to negative 4. Equation 5 then is going to tell me what q equals. That's going to equal 20 on that side. So that's 50 plus 2q equals 20. So that's negative 30, that's negative 15. And then if I go to equation, I kind of want to use equation 2, but it's got a negative c in, but we'll go for it anyway. Equation 2 says 1 minus 4 minus 15 equals 2 minus c. So that's negative 18 equals 2 minus c. So c equals 20. So I appear to have my solution set. P equals negative 4, Q equals negative 15, M equals negative 2, C equals 20. I should check that they work in some of the others. If I look at my first equation, this is 25 plus 20 minus 15, and that's compared to, well, what is that first? That's 30. Minus 5 times minus 2 is 10, which is 10 plus 20, so that works. In your checking procedure, you should go back and check all of them. As this video is now reaching quite a long one, I'll leave that checking for you. Not a satisfying final part of the question, if I'm honest. That felt like the question was building up. Certainly part I led into part II, led into thinking about the graph, which led into thinking about the asymptotic behavior and having to put this V shape in the right place for part 3. It felt like part 3 should have been the end of the question. Part 4 just, unless, and I'm certain there is a better way to do part 4, and I would like to know what that better way of doing part 4 is, and seeing how it actually links to the rest of the question. How does part 4 link to all these square roots of quadratics? Looking back at it now, maybe I could have written this side as, down here, this side as the square root of a quadratic. You just square it and put square root over it. But then this isn't linear on this side, so it just doesn't feel like it matches. I may have a look at another solution after I finish recording this, because I feel like there's something really clever I've missed in part 4. But here's a solution that hopefully helps you get to a strong point as well. The rest of the playlist here will continue to be populated with the rest of the questions from this step 3 paper. And good luck as you start to try them yourselves.